Hello, guys. This is 5.1, distance and accumulated change. So in chapter 5, we're starting to get into another topic of calculus, which is called the integrals. And before we get into that, let's just start with some simple application type of questions and to get us ready for the actual integration. All right, so first we have a distance, speed, distance, and time problem. So we know that distance is equal to velocity times time, right? And now velocity, you can think about it as speed, right? How fast you're traveling, multiplied by how long you've been traveling, then that gives you the distance. All right, so let's look at this example. Suppose a car is moving with increasing velocity and that we measure the car's velocity every 2 seconds, obtaining the data, which is in this table. So the question is, how far has the car traveled? Now, since we don't know how fast the car is moving at every moment, we cannot calculate the actual distance. But what we can do is we can approximate or estimate the distance traveled. Now, the velocity is increasing. So if the car at time 0 is going 20 feet per second, that means between the first 2 seconds, 0 to 2, it has to be at least 20 feet per second, right? Between time 0 and time 2 seconds, the car has to be traveling at least going at least 20 feet per second for the first 2 seconds. Now, since distance is equal to velocity times time, in the first 2 seconds, we can approximate this by 20 times 2, which is 40 feet. At least 40 feet during the first 2 seconds, right? At least. All right, so we can do this to everything else. For example, between 2 to 4, it's going from 30 feet per second to 38. So at least the car has to be traveling at 30 feet per second. All right, so between 2 and 4, that's another 2 seconds. All right, so we can do 30 times 2, which is 60 feet between t equal to 2 and 4. Okay, and we do the same thing for the rest of them, right? So we can do it for these, do it for that and that, right? So notice that the time is always in 2 seconds. So we're going to take the lower speed. So the first one will be 20 times 2, which we saw earlier. Second one will be 30 times 2. And between 4 to 6, it has to be at least 38. So 38 times 2. And then 6 to 8, we're going to use 44. And then 8 to 10, we're going to use 48. Right? So when you add everything up, we get an approximation of 360 feet. Right? So the 360 feet is an underestimate of the total distance. Traveled during the 10 seconds period. Right? Because we are using the lower speed, right? At least 20 feet per second in the first 2 seconds and 30 between 2 and 4, 38 between 4 and 6, 44 between 6 and 8, and 48 between 8 and 10. Right, so we're using the minimum speed to estimate the distance. Right, so that's why this is an underestimate of the total distance traveled during the 10 seconds. Now, the actual distance travel is actually a little greater than 360, but exactly what it is, we are not for sure. Now, we can also do overestimate, which is, let's say, between 0 and 2. Between 0 and 2, we know that the car is traveling at most 30 feet per second, right? Because the car has to increase up to 30. And at time 2, that's where we take the information. So between time 0 and 2, the car is traveling at most 30 feet per second. And then we can use that to do the same thing, right? So 30 times 2 plus 38 times 2 plus 44 times 2 plus 48 times 2 plus 50 times 2. All right, that gives you 420 feet. Right, now this is going to be an overestimate, right? Because we're taking the max possible speed within the 2 second period, right? Because we don't exactly know how fast the car is going between like 0 to 4 or 2 to 4, any 2 seconds period. So this is the only way we can estimate. So we know that the total distance, the actual distance traveled is going to be greater than or equal to 360 feet or less than or equal to 420 feet. Right? Because 360 feet, that's an underestimate, and 420 feet, that's an overestimate. Right? And then, we can kind of take the average of this, right? 360 plus 420 over 2. That'll give you 390 feet, right? So this is an average estimation, average of the upper estimate and the lower estimate, right? So which may be a little more accurate, but exactly how accurate we're still not sure. All right, so let's actually take a look at this problem using a graph. All right, so we have the graph here where horizontal is the time and the vertical axis is the velocity. So if you look at the darker blue rectangles, these represent the lower estimate. All right, these part represents the lower estimate. You can see that it all the boxes is below the blue line, which is the actual speed that we're traveling. But since we are only taking an estimation, right? So here we're using the lower estimate, right? Lower estimation to find the distance travel. All right. So another one, the upper one is going to be the overestimate, right? Which is this part. That's the overestimate. Right. So overestimate, and in pink, that's the underestimate. Right. So what we can do is the velocity can be graphed by plotting the data, right? So the blue line is our actual speed, and all the rectangles in dark blue and light blue, they represent our estimation of um, of the distance traveled. Okay. Now, one way to make this estimation a little more accurate is instead of taking 2 seconds every time, maybe we can shrink down to 1 second, right? Right. So here we're doing measuring 2 seconds every time. Now, if we measured every second, maybe we can get a better approximation. And furthermore, what if we do half a second, right? Then we will get a better, even better approximation. But again, if we do shorter time periods, then that means there are more calculation involved. Right. So let's take a look at another picture of that. All right, so if the velocity is positive, the total distance traveled is the area under the velocity curve, right? So let's try to understand this statement up here, right? If we make the a time span very small, so here the velocity in the first one, 5.2, velocity is measured every half second. So you can see that we have thinner and thinner rectangles, and then the area for underestimate and overestimate becomes more accurate, right? uh, Fits a little better to the curve. Now, 5.3, if we measure using 1/4 of a second, then we get an even better approximation of the line, right? So the distance travel under the distance travel is actually the total area under the velocity curve, right? So the blue line is the velocity, and the area under the blue line is going to represent the distance traveled, which is what we have shown, right? We add up each rectangular boxes here to estimate the distance traveled. And now this is actually our goal. If we can find the exact area under this blue line, then that area can represent the exact distance traveled within this time span. All right, let's take a look at our first example. With time t in seconds, the velocity of a bicycle in feet per second is given by the function v of t is equal to 5t. How far does the bicycle travel in the first 3 seconds after t0? Okay, so we're riding on a bicycle, starting the time, and then we ride for 3 seconds with the velocity given by 5t. We want to find out how long we have traveled, right? So let's draw the graph first. All right, so 5t, let's graph a table. All right, so t equal to 0 and 3. 0 is 0, 3 is 15, right? So 0, 0, and at time equal to 3, we are at 15 feet per second, right? So this line, straight line, is going to represent our speed, right? Because 5t, that's a linear function, right? So the graph is just a straight line. Now, as we learned earlier, this is the graph of the velocity. Okay, so to find the distance traveled between time equal to 0 and 3, all we need to do is find the area under the curve between 0 and 3. Right, so we actually have a triangle, and all we need to do is to find the area of this triangle. Right, so this distance is 3, right? And this distance is 15, right? So to find the area of the triangle is just 3 times 15 over 2, which is about 22.5. Okay, so that's the area under the curve. So the area under the curve of area under the speed curve or the velocity curve is going to give us the distance traveled, right? So 22.5 feet will be the distance traveled between in the first 3 seconds. In the first 3 seconds. Okay. All right. So let's put what we were doing into definition and into our actual terms and notations. All right. In general, to approximate the total change from a function f of t, giving the rate of change at time t, we can construct a sum, right? Just like while we're adding all the rectangles, all the estimation of distance between times together. We use the notation delta t, right? So this triangle t is red delta t, right? The triangle is red delta. I use delta t for the size of t intervals used, and we use n to represent the number of subintervals of length delta t. All right, so what this is saying is, let's say I have interval, right, from 0 to, let's say, 10. And then we can cut into different pieces. For example, if I just cut into 2 pieces, right? And then from here to here, that will be a delta t. And from here to here, that will be another delta t, right? And we know if we just cut it into 2 pieces, the middle one has to be 5, right? So delta t in this case would be 5 and 5. And then n would be equal to 2 because we only have 2 intervals, right? 0 to 5 and 5 to 10. Now, of course, we can increase the number of intervals by doing a little more cutting, right? Quotation cutting. Right? Let's say I cut into 4 pieces. I get 2.5, 5, 7.5. Right? In this case, each delta t, right, would be 2.5, right? Delta t is 2.5, right? Because the interval in each delta t is 2.5. And in this case, since we have 4 intervals, n will be equal to 4. Right? And that's basically what we're saying. Now, of course, you can do 10 of them, right? You can do 20 of them. You can do as many as you want. All right, so let's look at example 3. If t is in hours since the start of a 20-hour period, a bacteria population increases at the rate given by f of t is equal to 3 plus 0.1 t squared millions of bacteria per hour. Make an underestimate of the total change in the number of bacteria over the time using different delta t's. All right, so let's take a look. So we are looking at, let's start with part A first. All right, so we're looking at a 0 to 20-hour period, right? And each delta t is 4 hours. That means we're going to have 5, right? 20 divided by delta t, which is 20 divided by 4. That's 5, which is our n, right? All right, so we have 4. So let's say 4, 8, 12, 16. Right, and each one of them is the delta t or 4 hours, right? Delta t or 4 hours. Yeah. Now we know that the bacteria is only going to be growing, right? It's not going to be decreasing, right? So in order to make the underestimate, we need to consider the minimum amount of bacteria in that specific interval, right? So for example, between 0 to 4, right, the minimum would be here, right? The minimum. Right? And between 4 to 8, the minimum will be here. Between 8 to 12, the minimum will be here in our 8. And then between 12 and 60, the minimum will be here. Between 6 and 20, the minimum will be here, right? So we want to figure out, we want to estimate, right, what the bacteria at 0 is and for 4 hours, right? And then at what it is at 4 for another 4 hours, what it is for 8 at 4 hours, and so on. All right, so let's do this. Actually have a table ready here. Okay, so at t equal to 0, we have 3.0. When t is 4, we have 4.6, and so on, right? Now to underestimate between 0 and 4, that's called that part 1, right? Underestimate part 1, right? It's a 4-hour interval, right? So we can do 4 multiplied by the minimum amount of bacteria between 0 and 4 hours is 0, which is 3, right? So multiply by 3, right? Which is 12, right? And then we do that for the second one between hour 4 and hour 8. Now between hour 4 and hour 8, that's another 4 hours span. And then we want to take the minimum between 4 and 8, which is 4.6. Right? That gives you what? 18.4. Right? And then you do the same thing for the rest of them, right? So let's do this. Let's call each interval a name. So 1, 2, 3, 4, and 5. All right. So to underestimate these, we're going to take the lower value of bacteria in each time frame. Right. So we will have 3 times 4, 4 times 3, plus 4 times 4.6, plus 4 times 9.4, plus 4 times 17.4, plus 4 times 28.6. All right, so 4 times 3 represents part 1. 4 times 4.6, that's part 2. 4 times 9.4, that's part 3. And 4 times 7.4, that's part 4. And then 4 times 28.6, that's part 5. All right, so if you just take a look at part 5, which is our last time interval here between 16 and 20, right? So between 16 and 20, the minimum amount of bacteria will happen at hour 16, which is 28.6. And we're assuming that it's 28.6, that's a minimum value, right? So it has at least 28.6 between 16 and 20 hours. All right, and multiply that by 4, and this will give us the underestimate. All right, and then multiply these and add everything together, you get 252 million of bacteria. Okay. All right. So that's part A. Now, of course, if you pick a smaller time interval, if you pick delta t to be smaller, now, of course, the better approximation we will have, right? So let's take a look at the graph. All right, so this is the graph for part A, right, where n is equal to 5. Total, we have 5 intervals, 1, 2, 3, 4, 5, and delta t, right, which is 4, means the width of each rectangle. All right, so that assuming that the blue line is the actual function, right, so we can see that if we look at the area under the curve, right, we still are missing these parts, right? These empty spaces that's between the rectangle and the graph. So these are our errors, right? These are the errors that we get by doing an underestimate, right? Right. So our goal is to minimize error and try to be as accurate as possible, right? So one way to do that is we are going to make our n larger, right? To minimize error, we can increase n, right, by cutting into more intervals. That will result in a smaller delta t. Okay, so let's look at part B. All right, so part B says we want to use 2 hours, right, and over a 20-hour span. So 20 over 2, that will be 10, right? So we will have 10 intervals. And then for part C, if we're doing delta t as 1 hour, so 20 over 1, that will be 20, which will have 20 intervals, right? So the more intervals you have, the more accurate your estimation will be, right? So let's take a look at the graph for part B and C and comparing with A. All right, so for part B, you can see that the width of the rectangle is now thinner than the first one, right? And then we have more of them, right? We have 10 of them exactly, right? And then we can see that the empty spaces now under between the curve and the rectangle is much smaller than in part A, right? We have these parts, right? Much smaller than part A, right? So we can say that when we have more intervals, then the better estimation we will get. Now, if we look at part C, I can see that the rectangles are getting really thin, and then you can see that the area under the spaces between the rectangle and the curve, they get much smaller and smaller, right? You can see a lot of different little, like there are like little triangles under the curve, right? So we can see that to minimize error, if we increase the n, we increase the number of intervals, which will make each interval smaller, then the smaller error we will get, right? So you can see comparing A, B, and C, you can see that the error is becoming smaller and smaller. All right. Last, where we're going to talk about something called the left and the right hand sums. So let me start with a picture. All right. And let's say we have a curve going like this, like that. Okay. Let me make it a little curvy. Okay. Like that. All right. So let's say I want to find the area between A and B under the curve. I want to find the area under the curve between A and B. Now, one way to do it is we can fit in rectangles like what we're doing, right? So let's do that. Now I'm going to, let's say I'm going to cut this into 3 segments, right? 3 intervals, n equal to 3. And then I'm going to use the left value, the smaller value of each interval as my reference, right? So between, in the first interval, the left value is A, right? So I'm going to use the function value at A and then form a rectangle like this, okay? And then between, in the second interval, I'm going to use this point, right? Form another rectangle, okay? And the last one, I'm going to use this point as my function value, right? So I have 3 rectangles now. I'm going to use these 3 rectangles to estimate the area under the curve, right? So notice that I always pick the point on the left of each interval. So this is called the left-hand sum. Okay. Now, if I do the right-hand sum, then it will be a little different, right? Let's say I have a similar, the same curve, right? Like that. Okay, like that. All right, and then I have A and B. Let's say here A and B, right? And then same thing. I cut into 3 intervals. But instead of taking the value on the left-hand side of the interval, I'm going to take the value on the right-hand side of the interval. All right, so for example, in our first interval, I'm going to pick this point and make a rectangle like that for my first interval. Okay, and the second one, I'm going to pick this point on the right to make a rectangle. And then the last interval right here. Okay, and this is called the right-hand sum, right? Because we're using the value on the most right to pick as our reference point. Okay? And let me show you a better graph using that's from the textbook. All right, here we go. All right, so between A and B, let's say we cut into 4 pieces, so we can do T0, T1, T2, T3, T4, and so on, depending on how many intervals you want. All right, so the left-hand sum, we're picking the left value. Right, in this case, it's going to be T0 right here. Right, make a rectangle like that, and make a rectangle like that, make a rectangle like that, and so on, right? So that's left-hand sum. Now right-hand sum, right, we're picking the value on the right to form a rectangle, right? So you can see that depending on the curve, actually depending on how the curve goes, we're going to have overestimate or underestimate depending on how the graph goes, right? So we can, there's a formula to add all these up. Actually, let me put the formula here. Actually, before that, let's try to derive everything from here. So let's look at the first one, right? So let's say this is T0, T1, T2, and T3, right? When we cut into 3 intervals, these are where our cutoff points are. All right, so when we use the left-hand sum for the first interval between T0 and T1, we've used the value f of T0, right? And then in the second interval between T1 and T2, we are using the value for T1, which is f of T1. And then the third interval using f of T2. All right, so let's just try to find the area of the first rectangle. Now we know that the length of the rectangle is f of T0, right? And the width is how big we make those interval, right? So in this case, the width is actually called delta T, right? The width for every rectangle is delta T. And then the value is going to be different, right? So if we try to add up the 3 areas for the triangle, the first area is going to be f of T0 times delta T, right? Length times width. And then the second one is going to be f of T1 times delta T, right? T1 because we're using the left value of the integral of the rectangle, right? And then the last one is going to be f of T2 times delta T, right? So each one of them will give us the area of the rectangle. Now, if you're doing the right-hand sum, then that will be a little different, right? Do the same thing, T0, T1, T2, and T3, right? So the value for the first rectangle is f of T1 now. It's not f of T0, right? Because we're doing the right-hand sum. Okay, let me write it over here, f of T1. And then for the second one, it's going to be f of T2. For the third one, f of T3. right? And again, each one of them has the width of delta t. All right, so the first rectangle area is going to be delta t times the height of the rectangle, which is f of t1. Right, so f of t1 times delta t plus f of t2 times delta t plus f of t3 times delta t. Okay, so basically we're just taking, depending on whether you're using a left-hand sum or right-hand sum, that is going to determine our function value, determine our length of the rectangle, and then the width will be the same for every rectangle depending on how many intervals you're taking. All right, so here is the formula for whether you're using left-hand sum or right-hand sum. Right. So first, let's talk about the sigma notation. Right. So sigma is basically means the sum. Right. You're adding all the terms together. Right. So let's look at the right-hand sum first. Right. Notice that we're starting with t1. Right. Let me go up a little bit. Right. So for right-hand sum, we're taking the right value, starting with the first rectangle, right? So that will be f of t1, and then f of t2, and f of t3, right? So the first one we're going to use is f of t1. That's what we have here, right? The area of the first rectangle, right? We're using the right-hand sum, so we're taking t1 instead of t0. Now, whereas if you look at the left-hand sum, we are starting with t0, right? Because if it's the left-hand sum, we're actually starting at the first value, which is a. In that case, it's going to be t0 as our reference point, right? So taking the left value of each rectangle, and the height of the rectangle will be f of t0, right? So f of t0 times delta t, that's going to be the area of the first rectangle. Okay, and so on, and up to the last one, which is f of t minus 1, right? That is going to be the height of the last rectangle. And yeah, that's the formula for that. All right, so that's it for 5.1. Now, of course, we'll do a few more exercise together on Zoom. And thank you guys. I'll see you next time.